So everyone come on in and we'll start the Bible class this morning. Welcome to Lakeside. We're happy that you're all here. Today is a continuation of the Case for the Creator Bible series that we've been going through. We took a week off last week for the lectureship, and we're going to finish up the looking at the evidence from astronomy this morning. So last 2 weeks ago, we talked about, what's the chance if you have to end up in the right type of galaxy. So not all galaxies are created equal. There's a lot of them out there that are very prohibitive towards life. We talked about how you have to be in a spiral because you have to have the movement. The movement of the stars around a central point creates stability, okay? So we learned there's a fair number of systems out there that are created in this spiral shape. We've learned that most, like 70% of them, have some sort of a spiral system. Then we started taking a look down at our own sun, and we took a look at what happens if you go one star class higher than our sun. We learned, we did one star class lower. We learned that if you get one star class lower than what we got in our sun, you end up with a tidally locked planet, and your planet basically burns up or freezes, depending on which side of it you're on. Then we looked at if you had to go one star class higher than our sun, and you basically get irradiated to death. You either get gamma radiation or X-ray radiation in such extreme forms that it'll basically zap the planet. So this week we are going through we're going to take a look at a couple other things. There we go, that's better. And we're going to try and finish up the case for astronomy today, okay? So not only do you have to be in the right type of galaxy to begin with, you have to be in a spiral galaxy. Not only do you have to be surrounding the right type of star, or you're dead, you have to be at the right age cycle in your star's system, okay? So as good as our sun is, it was not as habitable to life at every point in its expected lifespan, okay? So if you think about how stars are formed when hydrogen swirls together and concentrates itself to the force of gravity, and then it will ignite, and then it starts going through the fusion process, okay? So if you start at the very beginning, okay, down here at the far left, you have a sun that's not quite warmed up yet, okay? And so it will not even support life, even though it's going to be eventually the right type of star, okay? Now, scientists will tell you that our sun will last, 13 to 14 billion years, okay? But it only becomes somewhat habitable around like 3.5 billion years into its cycle. So if you happen to be in the right place, surrounding the right type of star, but your star is too young, it won't work. The same type of problem happens once you hit about 8 billion years. So it's not like our sun is uniquely suitable at all parts of its existence. Once you hit about 8 billion years, the fusion inside of the sun is going to become, it's going to have burned up most of its hydrogen, and it's going to start trying to fuse the helium together. And then as it keeps running out of the most abundant types of fuels, what happens is it's going to expand, and it's going to expand rapidly until it hits that red giant stage. And when that happens, it's basically going to get so big it's going to swallow Earth. It's going to swallow at least the first 2 planets in our solar system, and they think it will probably swallow Earth. Long time from now, we don't have to worry about any of that. We got other problems in the meantime. But it's not just enough that you end up around the right type of star. You have to end up at the right age of your star at the same time, okay? So you have roughly between 3.5 and 7.5 billion years to be, which is only 21% of its age span, okay? So Um, you only have 21% of several billion years, but still, it's not completely like you get the whole thing. All right, next step. You can't have a binary star system. So binary star systems are when two stars orbit each other. Okay? It's incredibly prevalent out there in the universe. What they estimate is between 50 and 88% of the stars out there actually rotate with another star system as they go through around. The problem with that is that you can't have any stable orbits for any planet if you happen to co-rotate with another star. Because what will happen is, as your planets get close to one star, they will form an orbit, and then as the next star rotates around, it will mess with it and it will try to drag the planets off of its orbit, and it will try to drag it to the other star system. Or it will just straight run into the other star. So, you can't have a binary star system, okay? These do not allow for stable orbits of planets either. All right, next step. This is kind of hard to read. It's so much better on your phone. Let me try and walk you through this. This is from a really cool National Geographic article. So, what this is showing us is that in our own galaxy, with our own star, so if we find the right type of galaxy, we happen to be around the right type of star, we happen to be at this correct age of our star, and we don't happen to rotate with two stars at once, okay? You have to be at the right place in your own galaxy if you want to have a chance of surviving, okay? So, what this is showing us is at the center of our own galaxy, you have large amounts of the heavier elements that you would need for planet building, okay? You have, sufficient amounts of iron, sufficient amounts of oxygen, sufficient amounts of carbon, and all of those things that would allow you to form a stable planet, okay? The problem is when you get to the center of our own universe, you get closer to, one, the black hole, and two, you have huge problems with the radiation problem, okay? So inside the center of all of these galaxies, the amount of radiation that comes from those is incredibly dense, okay? So you can't have the right star at the wrong place in your own galaxy. It has to be the right star at the right place in your own galaxy, okay? If you move towards the middle, you get kind of the happy Goldilocks zone within this. So you have, well, I'm sorry, here, let's go to the other side. If you end up on the outside of our own galaxy, you have the opposite problem. You don't have any radiation problems, but you also don't have any of the heavier elements that you would need to have a planet. You would get the ends of the spiral arms of our galaxy are almost entirely hydrogen and helium. And they can look at this from spectral radiation graphs, which is really kind of neat. So you can't end up on the ends of our spiral galaxy. You have to be somewhere in the middle, okay? So in the middle, you have enough of the heavier elements that you would need to build a planet and to get a stable orbit, but you don't have to worry about the radiational or orbital issues, okay? But it's not even that simple, even if you end up in the happy medium spot. If you look at us, we are right there. We are nestled right in between the Sagittarius arms and what is called the Orion spur. So we are not even in the middle of one of the arms of our galaxy. We're in this happy medium zone where we're not in either place. And that is actually really convenient for us as well, because the arms of the Milky Way galaxy are filled with radioactive clouds, and there are also areas of active star formation. So it's not enough that you end up in this right galaxy. You can't be at the center part of your own galaxy. You can't be at the end of your galaxy. And you can't be in the middle of one of the spiral arms in your galaxy or you're dead. There's a very, very finely tuned small window of life that exists inside any of these places. Otherwise, you will just be subject to forces that will destroy anything that tries to form. So if life is so automatic that it's going to form anytime you get the right conditions together, there's very few conditions inside a single galaxy which will actually lead to life. So, all right. You have to have a circular orbit of your own sun. So inside of this system, this whole thing swirls, okay? And some of the stars in there have a circular orbit inside the galaxy, and some of them do not. The estimates is that less than 10% of the stars inside the galaxy match our circular path and speed of rotation, okay? So you have to show up at the right spot in your own galaxy. And then your orbit of the sun has to somewhat match the orbit of the galaxy itself. Because what will happen is if you don't match the speed of rotation or the orbit of your galaxy as you're going around it, your sun will cruise through one of those spiral arms, one way or the other. Now, it takes a very long time to do that, but it will happen. And when it crosses one of those spiral arms, let me see if I can, there's the orbit of the sun going around the galaxy. If you happen to cross one of those spiral arms, you will go into one of those regions of active star formation, and you will get bombarded with radiation, or you will run into something else, okay? So less than 10% of the stars inside our own galaxy have the circular path and speed of rotation that they've measured, all right? All right, what about the distance our Earth is from our own sun? Okay, what happens if you're too close? You fry, you burn up. What happens if you're too far away? You freeze to death. That's exactly right. So, these are the habitable zones that have been estimated in our own solar system, okay? Depending on which measurements you take, sometimes they include Mars in it, although Mars' orbit is not circular, so it won't stay inside the habitable zone for its entire orbit. And Earth is on the inner region of the habitable zone. So if you take the entire amount of space that we could have shown up in, from going all the way up to Mercury, all the way out to Neptune, poor Pluto didn't make it, and you measure all of that distance, and then you take the range which you could survive in, Earth's orbit is in 1.63% of the entire distance of our own galaxy, our own solar system. There's 1.63% of the amount of space out there which you won't freeze to death and you won't burn up. It's a very, very tiny amount. All right. Earth's atmosphere. If you look at the atmospheres of the other planets inside of our solar system, at the ends of the solar system, you have the gas giants. And they're all called that because they're made up almost completely of hydrogen and helium, if you look at those things. So it's really hard. I don't know of a study that's been able to look into like Jupiter or Saturn to see what's beneath them because all of the clouds are so opaque. At the other end of it, you have the terrestrial planets and the rocky planets. Most of them or 2 out of the 3, have almost zero atmosphere. So Mercury has 1/10 trillionth of Earth's atmosphere, all pretty much none. And the same problem is with Mars. So Mars's atmosphere is almost completely made up of CO2, but it's only, again, 1% of Earth's atmosphere, okay? There's not very much of it at all. Venus has the other problem. Venus is 93 times stronger than Earth's atmosphere. So you have to, what happens if you show up and you're on Earth and you're at the right place in our atmosphere, I'm sorry, you're right place in the solar system, but you don't have an atmosphere? What happens if you end up like Mars and like there's very little clouds, there's very little oxygen floating around, very little nitrogen? You can't survive. So if it's made up of that much CO2 like Mars has, like it's not breathable and it's even probably too concentrated for most plants to be able to survive in that system. The second problem is like without the atmosphere, like we're going to be subjected to, like you don't get any of the protection that you would from our current atmosphere. So most of the sun's rays and radiation are blotted out by the protective atmosphere that we enjoy on Earth. And if you don't have those systems, it becomes much harder for you to survive. All right. Problems if you change the orbit of Earth, okay? So Earth's orbit is almost completely circular. It varies from circular by a little over 1%, okay? If you look at, we're the red circle in that thing. So and what happens if you change the circularity of the Earth's orbit?
The temperature extremes go up.
The temperature extremes go up, exactly right, yeah. So as you get a more, what's called an elliptical orbit, you get more of this football shape that you see down here. You might be in the nice happy Goldilocks zone in between freezing and burning up for part of the year, but if you slingshot out and you spend some time outside of that, your whole planet's going to freeze to death, or it's going to get slingshotted in too close to the middle of it. And so you not only have to be at the right spot in your own solar system, you have to be there continuously, or you're going to die. So let's mess with it a little bit. Let's say, well, we didn't get completely circular. Let's say we got a little less than circular. Okay? If you look at this was run by the University of Pennsylvania at a 30% orbital eccentricity. So that's more like this one right here. So it's not super wonky, but it's still not completely circular. It's like the 0.23 system, okay? You can kind of see where it's starting to curve around the edges a little bit, but it's still mostly circular. If you do that, this is what your Earth would look like. Most parts of South America, Africa, and Australia will heat up to 140 degrees during the summer months. This is the extreme edge of the orbital eccentricity that they estimated a planet could survive. When they ran this by climate scientists, they said, what did climate scientists say? How much hotter can the Earth get before there's catastrophic climate change? What do they typically quote in the newspapers and stuff like that? 2 degrees. That's exactly right. And then they say at 3 degrees, the amount of hurricanes we're going to get, the amount of, floods, the amount of all of those things get incredibly dense. This is talking 15 degrees average Earth temperature increased. So this is 5 times the amount that they are quoting for catastrophic global warming and global climate change. Okay. So they also ran one more at a 0.7 orbital eccentricity. And at this point, this is much more like the football shaped. So in January, most of the world is frozen, and by March to May, most of the world is literally burning up higher than a boil, higher than 240 degrees, and then it goes right back to freezing. So, all right. Right planet, right solar system, right star, right place in that galaxy, right age of that sun, right orbit, okay? Here's something else that's really interesting, okay? You have to have a lot of brother planets out there, okay? So if we looked at that orbital eccentricity chart, where your chances of developing a nice circular orbit around your host sun is really dependent upon how many big outer planets that you have out there. Did you have a comment, George?
Go ahead. I'll ask. I got a question for you.
You got a question for me? Okay, cool. So this is a mapping of all the planets that we've been able to catalog so far. So if you look at NASA's website, they've got a little over 5,000 planets, and their rough orbits and the how many are forming around a single sun or a single star system out there. Okay, and what they found is if you have a single planet orbiting a star, it's all over the place in terms of its orbital eccentricity. So if you look at this first one right here, where it just says one planet, okay, that's one planet forming around a single sun, okay? And then you look at the orbits that happen on that chart, and they're all over the place. Some of them, you want the orbits that are closest to 0. That's what you're going for in this chart, okay? If you get underneath this blue line, there's a decent chance that you could survive. Anything above the blue line, and you're probably dead, okay? So if you have a single planet, and it's orbiting your star, your chance of having a circular orbit is very, very low. If you see, there's orbits out there that are all the way from 0 all the way up to almost 1. So an orbit of 1 is almost a thin line. It's so squished elliptically wise that it just slingshots like this, goes very far out, and then it just comes right back on the other side, just an incredibly thin line. Okay? What happens if you have 2 planets? The 2 planet systems actually help stabilize each other. So if you look, as you add more and more planets, they all start to help each other out. They all start to get the orbits where they're much more circular. So as you go to 2 planets, the most that they've been able to find is an orbital eccentricity of about 75%. As you go to 3 planets, it goes down to 50%. As you go down to 4 planets, and 5 and 6 in this case, you get about 0.3. And then there's a couple planets, a couple star systems, where you have 8 or 9, which is where ours fall. So what happens is if you end up in the right place, the chance of you forming a circular orbit, if you don't have those helper planets out there, is very low. So you can't just show up and just have a single planet forming around the right star, or you won't make it. You have to have other planets, and crucially, the bigger planets need to be on the outside of your solar system, okay? So we've got Jupiter, Saturn, Uranus, Neptune. All of those are incredibly huge relative to Earth, especially Jupiter. And what they're doing is on the outside of the solar system, they're basically acting like galactic vacuum cleaners, okay? So whenever they go through an area of space, the amount of gravity that they control will basically suck asteroids into the center of those things, and they will clear out those sections of space. So if you have a rogue asteroid that's starting to come into your solar system, and it passes into the the gravity zone of Jupiter, it will just suck it in, and it won't have a chance to get to the inner parts of the solar system where it could wreak havoc with us. So you got to end up in the right place, and you got to end up in the right place with brother planets to help you out. Otherwise, you don't form a nice circular orbit, and you don't get the protections of them having to clean out the asteroids and everything else for you. George, you want to say something?
I want to add another waggle to your discussion on
Okay.
temperature for habitable life. We know that, I think, I'm just going to confine this to our solar system. I think all of those planets that rotate around the sun rotate themselves on their own axis. And we know that our Earth does not rotate on a truly vertical axis. It's off about, I think, either 5 or 7 degrees. And that rotation off that number of degrees causes our seasons.
Correct.
Do you know if all of those planets rotate at a tip, not on true vertical?
No, most of them don't actually.
And what effect would it have on Earth if we were true vertical?
So you wouldn't have any typical seasons as we know them now.
That would mean that the North Pole would be, and the South Pole would be colder, wouldn't it? And the middle of the Earth would be warmer.
Mm-hmm. All the time.
Thank you, sir.
Yeah, for sure. Yes, ma'am.
This is the basis of centripetal force, basically, because if you, upon other things, and you're talking about temperature, but so many things are factored in with just the one orbit of Earth, if you just look at Earth's orbit. Now, as you mentioned, each of the planets helps for a more steady type of centripetal force, right?
Right.
But if you change that just slightly, I mean, just thinking about force and acceleration, think about torque, your cars, right? Your car can't drive if it has a non-circular tire. Have you ever seen a car drive with square tires? Or if the tire is ovular, it's going to...
Or if it's flat.
Exactly.
Yeah.
So when it comes to this force, it factors everything. We will feel it. Plants will feel it. We won't be steady. Time would feel it. We are just the basic principles of everything that we're ruled under, time, physics, biology, math, everything cannot sustain and function, let alone the ozone, the atmosphere, and the temperature difference, let alone that. You can't function. Time would almost nearly cease to kind of exist in a sense, because you feel this, the basis of everything you feel, and gravity would be so off that nothing would work anymore.
Yeah, you'd get pulled in all these directions. Yeah, absolutely.
Hey, Lance, this is all based on Newton's gravitational laws too, right?
For sure.
Yeah, because objects are attracted to one another by a certain force,
Right.
depending on their mass.
And their mass, depending on the mass of the two objects. Yep, exactly. All right. So this is, if you look at our own solar system, this is the eccentricity of our own planets, okay? The really nice thing about all of these is that all of the huge planets inside of our solar system, especially Jupiter, are very, very low. So ours is, like I said, just a smidgen off of center. It's 1.7%. And Jupiter's is a little over ours, just 4.8. What also happens is if you have those large planets, but one of them is kind of wonky, if one of them has the flat tire problem where it kind of just doesn't form an exactly circular orbit as well, what happens is Jupiter is so large that as our two planets hit this spot where they go around the sun and they get close enough to each other, what happens is Jupiter is so large, it would actually take us off of our circular orbit. And so it would mess with us. So you got to have the right number of planets that are out there, and then those planets have to be on the outside of the solar system, and then they have to be circular themselves, or they're going to mess with you on your inner part of the solar system. They said that if Jupiter's orbit became greater than the 0.10% value, it would the outer solar system becomes rapidly unstable. And what's really neat about this is you can take all of these things with the known physical constants, and so you can take a computer simulation and you can mess with all of these things and you can see exactly what would happen. Because we understand all of the orbital mechanics, we understand all the forces of gravity, we understand all the distances between all of these things, and so you can take a computer simulation and you can just tweak these things. And when you do that, they find that if you get Jupiter's orbit just 0.10 or higher, the entire solar system devolves and just crashes. Everything gets messed up pretty quickly.
This is evidence of a designer that put these things in perfect
No,
places.
Lane. We got super lucky. We're all super lucky. We're just talking about luck today. All right. As good as our own sun is, and we talked about how it's at the right stage in its life cycle. We talked about how it has the right orbit around our own galaxy. We talked about how it's the right star class so that we don't freeze or burn up. The other problem is our sun is still catastrophically detrimental to life, except for the fact that we have a magnetic field that goes around it. So the best estimates from scientists is that magnetic fields are caused by swirling iron inside of the Earth's core. Okay? So where does the swirling iron come from? The scientists think that it's made up of decaying uranium inside of the middle of the Earth. Okay? So as uranium decays, it's basically kind of a nuclear reactor inside there, is what they estimate. So the uranium decays and it puts off huge amounts of heat. And when it puts off this huge amounts of heat, what happens is the iron in the core circulates around the inside of it. And whenever you have iron that circulates, it will generate its own magnetic field. This magnetic field, we all know, protects us from a lot of the adverse effects that the sun would generate. Even being in the 1.63% of Earth of the solar system that we could survive in, we're still close enough that there's a lot of things that the sun would shoot at us that would mess us up. So as the sun shoots all of its rays at us, if we didn't have the magnetic field, what would happen is all of the pieces of solar radiation would slowly strip off the ozone layer that also protects us. And you just get to this point where even though you're close enough, you could still be irradiated to death inside your own star system. Okay? In order to have a magnetic field, you have to have the right size of planet. Okay? So, yeah, that's... So, if you think about Mars does not have any magnetic field. Mars is about, what is it, a tenth the size of ours, or a ninth? Mars is tinier than ours, okay? So if you get a planet that has the right amount of all of those things, but it's not the right size, it won't be big enough to sustain the reaction inside of its core to create the magnetic field, okay? So if you have a planet that happens to have the right composition, happens to have enough iron inside of its core, happens to have enough uranium inside of its core to sustain a reaction to generate a magnetic field, but it's not big enough, the reaction will never start. And so therefore you will not have a magnetic field to protect you, even if you have the right elements inside the middle of it, okay? Your planet has to be the right size. But this is also another one of those Goldilocks problems, because if your planet is not big enough, you don't get the reaction at all. If your planet is too big, you have the opposite problem. Once your planet hits a certain size, it will basically attract so much atmosphere that nothing on the surface will be able to survive. So you have to have like this happy Goldilocks zone of just the planet's size, independent of the composition of the planet to begin with. So you have to have the right amount of elements inside of the thing. It has to be the right size, so that you get the necessary amount of an atmosphere without killing you off at the same time. Earth's moon is critical to our survival. So basically what the moon does in terms of just like the biology of like the oceans and everything, has anybody ever, this is probably an older thing, but slept on a waterbed? Yeah, those used to be a big thing. Seems crazy to me because like I roll over a lot in my sleep and my wife would just be like, quit moving, you know, so, which is like impossible. But so anyway, when you sleep on a waterbed, what happens is the motion gets transferred to every part of it. So if you roll over on one of those things, you know, it just sends waves of water throughout this entire thing. And then, so the moon kind of acts in a similar manner. What the moon does is it's basically, as it circulates around and around the Earth, it's basically sitting there and it's pushing up and down on the water inside of Earth. And what happens is that causes all of these currents to flow through, which recycles all sorts of nutrients up from the bottom of the ocean, so where plants and animals can get to them. We did talk briefly, George, about the Earth's axis. If you don't have a moon and you it stabilizes the tilt of our axis. So Mars, Venus, and Mercury have huge amounts of orbital tilt. So like right now, we're at this like 23% tilt on ours. The change of axis between the inner three planets is much more extreme. Theirs vary by upwards of about 60%. So you can be facing up and down right now, but then the planet, as it keeps drifting around the sun, will just keep doing more and more and more of this. And I can't remember one of them. I think it's Venus. I think Venus is actually completely inverted. It looks like it's up and down, but it's actually, they know it's actually completely upside down at this point. That's correct? Yeah. So, and because of our moon, our tilt only changes by about 1.5%. To give you an idea of how crazy 1.5%, it doesn't seem like it's very much. They think that the last ice age was caused by when we were at one part of those tilts. So if we were at 23% and we went to 24.5%, they think that is the difference between ice age or not ice age on side of Earth. Okay, we talked about the mass of Earth. So here's the other thing. Let's say you have enough of all of the things we talked about before that. You also have to have the amount of water on Earth that we have to survive. But the amount of water that exists on Earth, if Earth was a flat planet, is incredibly immense. If Earth was completely flat all the way around, and then water was on the outside of it, the entire surface of the planet would be covered in 2 miles of water. If you don't have tectonic plates, which shoot up sections of land into these mountain systems, and they force other parts of the planet deep down into the ocean, you have this entire planet that's entirely encased in water, but nothing will survive on it. The entire surface of the planet would be covered in 2 miles of water if you don't have tectonic plates, okay? Also driven by having the right amounts of all of those things. All right, what we got? I heard the bell, so, all right. Yeah, that's impossible to read. So, what's the chances of all of these things happening? It's functionally equivalent to 0, okay? You have to have a spiral galaxy. You have to be in the middle of a spiral arm. You have to have the right distance from other large galaxies. You have to be around the right star's sun class. You have to be in the right age of that sun. You have to have a circular orbit of less than 10%. You can't be in a binary star system. You have to be the right distance away from the sun. You have to have a circular orbit. You have to have a circular orbit of the large outer planets. You have to have just the right number of large other planets. You know, you have to have a moon to stabilize your tilt. You have to have the right atmosphere of Earth. You have to have tectonics, the water system, the crust thickness, which we didn't get the chance to talk about. I know y'all are sad. But all of those things, if you look at that and you do the math, this is 6.29 times 10 to the minus 14th, or 6 planets in 100 trillion might get there, okay? So at the beginning of this astronomy lesson, we learned that there are between 200 and 400 billion planets inside of our own solar system. So what's the chance of, so if you look at all of these things, how many planets would we expect to have survived the gauntlet and end up in the right places with all the right things? Less than 1 planet is what you come up with. It shouldn't have happened. Even that we exist at this razor's edge of death everywhere. Like, like the chance of us freezing or being burned up or getting hit with an asteroid or, there's a billion ways to die in your own solar system. It's quite easy to end up dead. And so your chance of having a single planet that survives all of these things is, or 6 planets in 100 trillion. So less than 1 planet is expected to have met all of these criteria by the time you get to the end of it. So this is what we call, well, they're like, sometimes you'll hear these people on news podcast or whatever you're going to listen to, and they're like, well, yeah, but if you give enough chances out there, like, this is the whole monkey on a typewriter argument. If you give enough monkeys enough typewriters and they give them enough time, they can reproduce Shakespeare, which is actually not true. But yes, ma'am.
It's funny. I stumbled upon a small clip of a commentary about there's this show, I think it's called something Sheldon or something like that. But that part of that show apparently said where it talked about just the stars, planetary motion, Earth's orbit, and how amazing it is that everything happens so precisely to where we can live and habitate this planet specifically. The funny thing is, too, is you went over the magnetic, the magnetic field of the Earth, right? That's the basis of how we get our electricity. So, wow, it's smart that somehow a non-sentient planet was able to help us form electricity. Just
Right.
like computers are based off our brains, just like cameras are based off our eyes. So interesting and unique. And uniquely enough, astronauts actually can only stay on the moon for a certain period of time because they're outside of Earth's protective radiation field, magnetic field.
Magnetic field, yeah.
And if they ever had to, I mean, their likelihood of cancer and many other things and mutations increases because of the higher amounts of time that they spend on the moon.
Right.
If anything, they'd have to burrow into the crust, into the moon, to be able to survive whatever research they need to survive.
Exactly. Exactly. Yeah. So to just give you one last thing, and then I'll let you guys go. Like, if I gave you guys 1/1,000,000th of a penny, it doesn't let you go to Starbucks and suddenly get the latte when you weren't going to get the latte before. You know, I can give you 1/1,000,000th of something, and you would basically say, "Thanks for nothing," which is exactly right. I gave you something that was functionally equivalent to 0. It didn't help you. And that's the chance of finding a planet out there. It's functionally equivalent to 0. So there has to be something else that happened to nudge all these things in our right direction. Thank you all. Appreciate it.